Today I'm going over magnets for GCSE Physics today. I'm going to go through the basic magnetic rules, and I'm also going to go through what a permanent magnet is and what an induced magnet is, okay? So if you want the notes on this topic, don't forget to check out my resources on the My EdSpace website for worked examples, TikTok, questions, loads of stuff like that. And you can have a look at the link in the description of this video to see about joining my live lessons. So let's jump straight in. Now, I'm hoping that you know that a magnet has got two poles. It's got a north pole and it's got a south pole. Now, you're going to talk more about like magnetic field lines and strength and stuff like that in my next video. But all you need to know at the moment is that where we've got the poles, that's where the magnetic force is strongest, okay? Now, we have a rule in magnetism which says like poles repel and unlike poles attract. So let's have a look at what this means. So here we've got a north pole and north pole facing each other, okay? So we would call them like poles because they are the same. So these guys are going to repel. That means that this one's going to push this one that way, that one's going to push this one that way, and they're going to move apart. Now, the next one that we've got is a north pole and a south pole. These guys would be unlike poles, okay, because they are different. So these guys are going to attract. The north pole will attract the south pole will attract the north pole, and they're going to move together. The only other combination that I can have is if I've got a south pole and a south pole facing each other. And again, these guys are like poles because they are the same pole. So that pole will repel this one, that pole will repel this one, and they are again going to move apart. Now, I've got two different types of magnets. I've got a permanent magnet and an induced magnet. So a permanent magnet is, as the name suggests, something that always has a magnetic field. So it will always be magnetic, okay? A magnet, like a bar magnet here, for example, it's very difficult to get it to lose its magnetism. We can heat it up really hot, or we can hit it really, really hard with a hammer. This might be why your teacher has asked you not to drop your bar magnets if you've used them before in class, because it can weaken their magnetic field slightly. But fundamentally, once these guys are magnets, it's really difficult for them to not be magnets. So they would be described as a permanent magnet because they're always going to be magnetic. Now, an induced magnet is slightly different. It's only magnetic inside another magnet's magnetic field. So these induced magnets will only be magnetic if they are near a permanent magnet. So these guys are going to be made out of my magnetic materials. There are three magnetic materials that you need to know, which are iron, nickel, let's try and spell nickel correctly, shall we? There we go, and cobalt. A really common misconception is that copper and aluminium are magnetic. They are not, okay? They conduct electricity, but they are not magnetic materials. Now, steel could also be on this list, but I'm not going to add it because steel is made out of iron, so that's why it's magnetic. As long as you know that it's iron, nickel, and cobalt, and you know that steel is made out of iron and other materials, you're going to know that steel is magnetic. So let's have a think about how these induced magnets work. So we're going to imagine a paperclip on the end here. So the paperclip's always going to stick to the pole of the magnet because that's where the magnetic force is the strongest. Paperclips are normally made out of iron, so they can be attracted by a permanent magnet. They are induced magnets. For this end of my paperclip to attract to this north end here, I must have induced a south pole in the top of the paperclip here. So it means that this end must be a north. If I then stick another paperclip on, that would be a south, this would be a north, because remember, we've got to have Unlike poles, they've got to be different to attract. Now we're going to imagine that I'm going to take these paper clips off this end, pick them up, and put them on the south end. Now they're still going to attract because magnetic materials can only ever be attractive, okay? Induced magnets can only ever be attractive. They cannot be repulsive. You've never seen a fridge magnet repel from a fridge, have you? They always stick onto the fridge. So, if I were to take these paper clips off and move them, I would induce now, because this is a south pole, I'm going to induce a north at the top end of this paper clip. So that would be a south. So if I stick the second one back on, that would be a north, and that would be a south. And this is how induced magnets work. I really hope you found this video useful. Don't forget to check out my resources on the My EdSpace website if you want the notes on this topic or you want any more information about any of your GCSE topics. You can check out the link in the description of this video to have a look at joining my live lessons. And whilst you're there, don't forget to subscribe to this channel. I'll see you soon. Take care. Hi kids, welcome to my video on GCSE magnetic fields. And this is a super common topic for them to ask in the exams, so make sure you're listening. Now, we're going to start by thinking about what a magnetic field is. So a field in physics isn't a green thing with grass and a gate. It's any area where a force is experienced. So when we're thinking about a magnetic field, it's any area where if we put a magnetic object or another magnet there, that is going to feel a magnetic force. We know this from common sense. If I have two magnets, I hold one over here and one over here, they're not going to act on each other, right? Because they're not in each other's magnetic fields. As I bring them closer, their magnetic fields are going to start to overlap. Once we've got one object inside the other's magnetic field, it's going to start to feel forces. As we bring them closer, they get further into the field, those forces are going to be stronger. So you need to be able to reproduce the shape of the magnetic field around a bar magnet. Now, I always like to think of this as looking like a jacket potato. So we're going to draw a bit of potato up at the top, a bit of potato at the bottom, and then three ends. Now, the magnetic field around a bar magnet always goes out of the North Pole and into the South Pole. So out of the North, into the South, out of the North, into the South, like that. What the examiner is going to be looking for, if they ask you to draw the shape of a magnetic field around a bar magnet, is that you've got the same number of lines on the top and the bottom, so it's kind of symmetrical. They're going to want 3 lines at least, and they're going to be looking for those arrows going in the correct direction. Now, there are 2 ways that we can find the shape of the magnetic field around a bar magnet. That is either using iron filings or using a plotting compass. Remember that a compass is just a small bar magnet that's free to spin. So if I put a compass anywhere in this bar magnet's magnetic field, it's going to align with the magnetic field and show us the direction. So that is the main advantage of using a plotting compass as opposed to iron filings, is that a plotting compass will also show you the direction of the magnetic field. Iron filings won't necessarily. Right, so not everything is a magnet. Okay, but some things can be magnetic without being a magnet, and that is what we call induced magnets. So there are only 3 magnetic elements, okay? They are iron, cobalt, and nickel, okay? Those are our 3 magnetic elements. There are no other magnetic elements. A really common misconception is that students think that aluminium and copper are magnetic. They are not. Or students think that all metals are magnetic. They are not, okay? Our only 3 magnetic elements are iron, cobalt, and nickel. Now, the way that these guys become magnetised is they become what we call induced magnets. So if I've got, let's say, an iron paperclip, and I put it in the magnet's magnetic field, it's going to cause my paperclip to become what we call an induced magnet. So it becomes a mini magnet all of its own. So if it's attracted to the south end, it'll get a little north here and a little south here. It becomes an induced magnet. If I take that paperclip, though, outside of the magnetic field of the bar magnet, it's no longer going to be magnetic. It's no longer going to be an induced magnet. So that paperclip then can go and pick up another paperclip. If I put it back inside the magnetic field of this bar magnet, then it could pick up another paperclip. Again, inducing a little north and a little south. Now, if I took these paperclips off this end and took them to the other end of my magnet, remember that magnetic materials are always attractive. So what will actually happen is that I get a south, a north, a south, and a north. Will induce different magnetism in them, depending on which pole of the magnet we put them close to. Now, this works best at the poles of the magnet, because that's where the magnetic field strength is the strongest, okay? These field lines can actually help us to work that out, because a field is always strongest where the field lines are closest together. So for a bar magnet, the field lines are closest together at the poles, so it's the poles that are the strongest part of this magnet. Right, let's talk about our magnetism rules then. So if we've got two permanent magnets, so things that are always magnetic, like bar magnets, and we put different ends together, different things will happen. So if we put the north ends together, they will repel and the field lines will bend and look a bit like this. Notice that the field lines don't cross, okay? It's showing those magnets bending away from each other. They're going to repel. The same thing happens, actually, if I put two south poles together, except for the field lines are going in the opposite direction, but the same thing still happens. The south and the south will also repel. The only ends of the magnets that will attract are the unlike poles, so north and south. We get a field that goes like this, so it's straight, and because the field lines are staying at the same distance away from each other, it's a uniform magnetic field, so it's the same strength all the way through. And here it shows that these guys are going to attract together. So our overall rules of magnetisms are that like poles repel and unlike poles attract. And there you go. That is our basic rules of magnetism and magnetic fields done for you. So if you really want to improve your grades in physics, I think the best way of doing that is to join in with our My Edspace live lessons. There's a link in the description of this video if you want to go and check out what those are all about. Equally, if you just want the notes on this topic, you can also check out my resources on the My Edspace website. And don't forget to subscribe to this channel so I can carry on making more content just like this for you. I'll see you soon.